I'm going to talk to you about reservoir computing, but implemented in skyrmion fabrics. And the first thing I'd like to do is to recognize Karen and Daniel, who my collaborators on this. We've been working on it for several years. At least Karen and I have, and Daniel and I the better part of a year. So anyway, it's a joint effort, which I think is quite interesting. So the first couple of slides I always devote to motivational slides. And frequently that takes the form of Moore's law is ending, the sky is falling, yada, yada, yada. You need to pay attention to what we're telling you. But I'm going to try to motivate you a different way. I'll make the statement that as a society, we're starving for information but drowning in data. And anything that can help us resolve that issue, give us information from data, is worth a lot of money. And there are a lot of companies that have gotten rich by realizing that, Google, Amazon, to name just two. But what I'd like to mention to you is that there's a well-respected market analysis company called Statistica in the US that's just released a projection for what the total world market will be for artificial intelligence over the next 10 years. Now that's all forms of artificial intelligence I'll mention, and that includes a lot of different things, but the numbers are staggering. They project 148% annual compound growth rate. And that, if you know any businessman, you quote that to him, it's going to make his eyes light up and he'll think you've been smoking something. But what that means is by 2025, the total world market for artificial intelligence will be something like $7 trillion, 7 trillion US dollars. And that's to help you understand just how amazing that is. The total gross world product in 2025 is estimated to be $100 trillion. So this is going to be 7% of the gross world product within just 7 or 8 years. Now this is truly astounding. If you dig a little bit deeper, you'll see this covers a lot of different things, all of which are just exploding right now. Security, autonomous vehicles, human-machine interfaces, drones and robots, silicon platforms. You can read them and understand. Each one of those is just exploding. You read articles all the time about how dynamic these are. It's one reason why Google and Amazon are paying new PhDs out of Stanford in data science upward of $300K a year as a starting salary, because they know that money is to be made there. So I hope that is a motivation for young people. You won't see reservoir computing anywhere on this list, but a rising tide raises all ships. And there's going to be a lot of research money coming out trying to figure out from the university communities, academia, how to realize some advantages here. And I'll emphasize what Mark said a few minutes ago. We don't have to compete with CMOS. We can be additions to CMOS. Industry is very comfortable with the idea of incorporating accelerators, accelerated chips. Some of you may remember that when we needed to get a floating point accelerator chip to add to your computer, or more recently, graphics chips. What happens is these chips get developed, and then they get incorporated into the processing. As Mark also said, some of these can be magnetic, because magnetic is a part of the manufacturable base right now. So With that said, yeah. So how does nature, we're talking about artificial intelligence, how does nature solve this problem? Well, it's had 20 million years of evolution to perfect that, and this guy knows what to do pretty rapidly. But if we use a state-of-the-art deep learning system, we'll feed in an image of a lion, and if it's well trained, we'll get out a reading after a few hundred milliseconds that yes, that's a lion. But there's nothing in here that can tell us that this lion is coming straight at me and I better move quick. And that's just beyond the capability of any kind of existing artificial intelligence that we have today. So that's a real need. Anything that can analyze real-time spatial temporal information and generate responses to that, there's a market for. So how does the brain do this? We've heard a lot of this already, but it's made up of neurons, axons, dendrites, synapses. It is a dynamic system. It is an asynchronous neural net. Some of its core operations are association, compare, exploration, exploitation, but it is a liquid state. That point has been made several times. So if you look at how it's done today in the big machines, you can do a lot with them, and a lot is being done, but they're made up of transistors, wires, inputs, Boolean logic gates. They're synchronous. That point was made early on. They've got to be changeable, and they have finite state. They step from step to step to step, and that's very different from the way nature works. So what I'm going to be talking about today is trying to reproduce some of the functionality of a human neuromorphic processing, but using a skyrmion fabric as the reservoir and doing reservoir computing using the formalism that's been developed for that. And just point out that this is liquid state, it's asynchronous, and those two things alone make it more similar to the human brain. So looking for a few additional clues from nature, oscillations are ubiquitous in the human brain. There are many published examples in the literature about oscillations in the brain being associated with cognition. And you see frequencies of the range of 50 to 70, maybe as high as 80 hertz. But these are recurrent loops that are oscillating, generate spikes, but they also play a role in synchronization and cognition. You can also look and see that there are actual loops formed in the brain. If you just trace it out, these are examples of what looks like well-formed loops, which are excited as part of the cognition process. So the takeaway message there is that loops are important. I'll mention one other paper I came across recently by Domini and Arab, which talk about the ocular motor issue, where how do we adjust our eyes to focus on what we need to focus on, move our eyes to pay attention to what we need to pay attention on. And they identified a particular region in the brain called the striatum, which is they associated with the readout function. In other words, this integrates examines the high-dimensional state space produced by the cortex and extracts the information it needs to move the eyes within and the head, both basically to respond to various stimuli. So I hope by this time you believe that recursive networks, recursive loops in nature are important. But the problem, as we've heard several times with recursive neural networks, is that they're very difficult to train. They're because of programming errors, that you use a backward error propagation, you have vanishing error gradients, you have exploding error gradients, you have bifurcations, and they're just notoriously difficult to train. So again, as we've heard several times in this talk or this meeting today, reservoir computing provides a mechanism to harness the power of reservoir computing, but do it in a tractable manner by being able to solve just a one-dimensional minimization problem. I should mention at this point that when you talk about reservoir computing, there are two types of systems. There are what's called liquid state systems, which involve spiking neural networks, and there's echo state machines, which involve changes in the resistance. And it's the latter we're going to be talking about. But if you look in the literature, you'll see that there are two types of machines. Oops. So again, we've seen numerous slides like this, but I just wanted to show it one more time. This is what reservoir computing looks like. You have the reservoir here, which is composed of a large number, hopefully, of nonlinear nodes, which have random connectivity to the other nodes in the system. Because it's random, some of the nodes will be connected recursively. So it's not a straight feed forward. This is recursively connected neural network. You have the input array here, and you have the output array here. You train the output array to extract the information that you need from the high-dimensional representation of the input images. You adjust the input arrays so that this reservoir is driven close to criticality. You want it close to chaos, but not chaotic. And again, that's important for biological systems, as we heard earlier. The output array is relatively easy to deal with because it's a linear regression algorithm that people know how to solve in a straightforward manner. So there are a few other requirements for reservoir computing to work that is important to note. There needs to be a fading memory time of the reservoir, and this should be related to the time scales of the input, and we heard some about that in the last talk that Mark gave us. The reservoir must be complex, random, with multiple degrees of freedom. And in general, the more degrees of freedom you get a sparser representation of the input in the high-dimensional space. It needs to be stable. In other words, it shouldn't change once we start training the output layer. You want it to respond approximately the same way to inputs so that the training neural network, the output neural networks, the training you've invested there can be reapplied. There needs to be echo separation. There has to be sufficient separation of the echoes, which has to do with the dimensionality of the high-dimensional space. And then you have to have the resolution capability of the output array to be able to recognize those. And the resolution is determined by the number of nodes that you have primarily. Okay. Now, I'd like to mention this. This is a critical, I don't think we've seen this yet, but this is a novel feature of reservoir computing that I'd like to mention because it really has some significant impact. It's called generalized learning. And what you see here is a set of image pairs where each image is some nonlinear transformation of the other. For instance, if you just look at the threes, you see a 3 right side up and you see a 3 rotated by about 90 degrees. Here you see a 3, and here you see a zoomed image of the 3. And here you see a 3 with noise added. And here you see the last one. These are different digits. So these are things that neural networks are frequently called on to do, is this image recognition. Now what reservoir computing can do is that it can memorize the relationship between pairs. In other words, if you take with the dual reservoir formulation, and I'll refer you to this reference if you want to see more, if you fed in a 3, the normal sample 3 in this reservoir, and then you fed in the 90-degree rotated version of the 3 into this reservoir, and you basically you concatenate these with your output array, where your output array is connected to both reservoirs. The reservoir will basically find that these rotated pairs basically all congregate in this area here, which is one region of the high-dimensional space. I should mention this is a low-dimensional representation of the high-dimensional space that was developed by Hinton and his colleagues at the University of Toronto and Google also. But it's a neat way to represent what's configuration, high-dimensional space and low dimension. But what you see is that the rotation of pairs is all here. And the black, for instance, is different pairs. This is where the 3 and the 2 show up here. The important point here is that you can train the reservoir for one set of digits, say 0 through 4. And then you can use this reservoir system on another set of digits where you don't have to train it. This reservoir system will work on digits 5 through 9, for instance, without additional training. So this is really fairly important. It's also fairly important because it allows us to identify, well, this image looks sort of like this image, but it's not an exact match. And it tells you how it's different. So this is a characteristic of reservoir computing that I think has a lot of potential value for real applications. So these are the equations for governing reservoir computing. I think we've heard about them a number of times. I won't go through them. The x tilde represents the provisional state of the reservoir. This is the input. This is the input weights on the input array. This is the input function, and this is the state of the reservoir at the previous step in time, and W is the weighting function, is the weights of the reservoir nodes. You then update the state of the system according to that equation, and then you solve for Y based on a simple minimization of the output compared to a known input, where you basically use a training value and a target value, and you minimize the output weights so you get a good match. Okay. Now the way we do this in practice is that if we notice, as we've been mentioned several times, this is a skyrmion fabric that we'll be showing you more, and this is what we're actually going to be using. But the idea is to excite the skyrmion fabric at a random set of points in the fabric, and then sample the output of the fabric at a different random set of points. If we were inputting an image, we'd have to chop up the image in slices, and we'd input one slice at a time into this reservoir and then analyze the state of the reservoir at that time. So I think everybody is aware of the fact that these have been implemented. This is the atomic switch network that they did a few years ago at UCLA. It employs memristive devices to basically implement an echo-state system. We heard earlier a beautiful example of using optics for implementing reservoir systems. This is real. I mean, it does work. And I don't think I'm going to spend any more time on that, because I think at this point people understand that, and I don't have to convince you of that. So now I'm going to talk a little bit about the skyrmion fabrics. These are the LLG equations. We've heard a lot about those already, so I'm not going to spend any time there. This is how the magnetoresistance is calculated. I won't say any more there. And then I'll get to the results, because this is where it's really pretty interesting. First of all, to do what we need to do, remember I said that the reservoir needs to be stable. So when you apply a current to the reservoir, you don't want the skyrmions moving, which they'll have a tendency to do. They'll have a tendency to drift. And that would change the response of the reservoir and the response of the system. So the first thing we had to do, or Daniel did, is basically he applied a grain structure to the reservoir, typical grain structure you'll see in many metals, heavy metals, and applied that, and then worked from that as the basis. What he did was he applied a uniform matrix of skyrmions. He started with a uniform matrix. He applied the grain structure, which basically set boundaries, basically potential boundaries that the skyrmions could move within. He thermalized that, let it relax, then hit it with another thermal pulse and let it relax again. Now you notice these last two look very similar. I mean, there's really very little difference between the two pulses, so that this is relaxed more or less to its equilibrium position, and it can be postulated that additional pulses or additional thermal effects would not change the reservoir too much. So, and then the other thing is to expose the reservoir to an input voltage. So what he did was applied a voltage, which is typical of the driving voltages that we'll be using, of 0.01, 10 millivolts and 50 millivolts, and observed the structure and saw that everything stayed basically where it was, and nothing moved very much. So just to remind you, this is the actual calculational domain that we're dealing with. We have either block or neo. We chose block skyrmions. But contrary to the photos I showed you earlier about what a reservoir computer looks like, we drove this at only 2 points, where there's applied a voltage between these 2 points and measured the response of the system to that applied AC voltage. And that's what we're going to focus on for the rest of the talk, because there's some very interesting results. So the first things we had multiple frequencies, but I'm going to show you two, one at 10 gigahertz and one at 1 gigahertz signals. So the first thing we did was apply two different pulse shapes, a sine wave. We applied a 10 gigahertz sine wave across the fabric, and then we applied a 10 gigahertz square wave. And what you see is that the system responds very cleanly. There's some ringing here associated with basically just doing the ferromagnetic excitation of the system, but that decays over something like half a nanosecond, which is typical of the FMR decay time of the system. We then put on a 10 gigahertz pulse train. The pulse train consisted of 2 sine waves, followed by 2 square waves, followed by 2 sine waves, followed by 2 square waves. And what you see here is there's 2 separate curves. There's the physical response, which means just the signal of AMR signal as a function of time that responds to these pulses. And it responds cleanly. There doesn't look to be any nonlinear effects. It basically just responds pretty cleanly to the input that was applied to it. Also, you'll see the gold or the yellow, and that's a linear reconstruction of the individual responses from the individual pulses that I showed you immediately previously. In other words, if you just take the individual response that I showed you previously, and then superimpose it with the individual response from that one, you'll see something like this. And you notice this does build up in time. The amplitude does tend to trace out basically there is an accumulation that has to do with the memory time of the system. But what you also see is that, again, the linear superposition agrees very, very closely with the physical response of the system. What that says is there's really nothing nonlinear and nothing collective going on in the skyrmion plasma. Now we apply a 1 gigahertz pulse, and here the situation is different. If you look at the response to a single 1 gigahertz sine wave pulse, you'll see there's a lot of nonlinearity. It's not a clean response. There's a lot of nonlinearity and probably some collective effects going on as well, to where individual skyrmions are exciting their neighbors, and there's a collective response being generated. Similarly, when you see the square wave being applied, you'll see a lot of, because the square wave has higher frequency components, you'll see some higher frequency components in the response function. But this is indication that something nonlinear is happening and something collective is happening. You'll see that even more plainly on the next slide. Here we have a pulse train again. We apply two sine waves, 2 square waves, 2 sine waves, 2 square waves. We get a sequences between a square wave and a sine wave. We get sequences between a sine wave and a square wave in sequence. And there are a couple of things to note here. First of all, the amplitude. This is a factor almost of 10 larger than the individual responses that I showed you on the previous slide. That's clearly an indication that something collective is happening, where basically one skyrmion response is exciting additional skyrmion responses. You'll also notice the gold here again is a linear reconstruction. And what you'll see is the amplitude of the physical response in this case is much greater than just a linear superposition. again indicating that something nonlinear and collective is happening in the skyrmion fabric. But there's more, and to see that, let me point out that there are some patterns here. If you run your eye across, just for instance, the black arrows, you see these all look pretty similar in shape. There's a very similar characteristic shape of this response. And what you'll also see is that these black arrows occur after two square waves are applied to it. Similarly, you see the red arrows. If you run your eye along those, you'll see very similar shapes of the red arrows as you go through the pulse. And again, you'll see that that's associated with a particular sequence. The red arrows is associated with the square wave preceding sine wave. Square wave, sine wave. Look here, you have a square wave, sine wave. Same pattern, square wave, sine pattern. Similar with the gold arrows. The gold arrows tend to look alike, and these are all identify the sequence of sine wave, square wave, sine wave, square wave. Everywhere you see a gold arrow, you'll look behind it, you'll see a sine wave and a square wave. One could argue, as a matter of fact, that what we're actually seeing here is some pattern recognition. Even though this is a very simple reservoir with only two contacts, rather than having multiple input and multiple outputs, what you're seeing is something that really is pattern recognition. If you just looked at this gold arrow, for instance, look at the shape of this response, someone could tell you that, aha, that was caused by a sine wave followed by a square wave. So that's again is demonstrating the memory of the system and the potential for doing real pattern recognition once we get for spatial temporal inputs. This is temporal inputs. They're not, but you have to get more contacts. You can excite the skyrmions to do spatial temporal recognition. So that's a highlight. If you look, okay. So I'd like to show you a little movie here. Yeah, if you watch, this is for the 1 gigahertz pulse train. And look at the skyrmions. There's really motion. Looks like there's some coupled motion in there. And this is, again, looking very biological. If you look at this looks pretty similar to the slides we saw, the movie we saw yesterday on bilayer lipid slides, which have some of the same motion. So let me run it for you again. No. Yeah. So it's worth just watching the motion of these. They're constrained motion. They're constrained by the grain structure that's in the problem, but they're really showing a collective motion that's responsible for the large amplitude response and the nonlinearity and the pattern recognition. So these are fairly small effects. Even so, as we heard 2 days ago, I guess, the magneto response, this is probably 4% of the magneto response, which may be 1% of the total response across the system. So should be measurable in the lab, and it is measurable. And that's what I'd like to show, just mention that this is an experimental observation. This jump in the magneto resistance here is caused by the presence or absence of one skyrmion in a manganese silicon nanowire. And and again, this is neighborhood of 4% change of the magnetoresistance. So this can be detected as it sits in the lab, but as far as making a useful system, that needs probably some additional work. But there are scaling paths. One of the things that industry loves is to have a scalable technology, which can go through multiple generations. So one way, simple way of scaling it is to increase the size of the system. This plot shows the amplitude of the response versus the length of the system. What I showed you was 500 nanometers system length, and this is about a 4% response. The average expectation is we made it twice as long, you get twice the response. That's not a good solution, but it is a solution. In addition, I mentioned that this is static magnetoresistance. They're dynamic. This doesn't have anything to do with electron transport through the plasma. Through the fabric. And it's very likely that there will be some additional effects coming in from the electron transport. What I'm showing here are some current paths that Matthias calculated early in this project, and they show some recursive, they hint at recursive flow. They don't show that absolutely, but they certainly hint that there could be some recursive flow in the electron transport as the electrons associated with the excitation flow from one side to the other. This is speculative. It has not been simulated in detail, but and it would require a great deal of additional coding to try and do that. So in conclusions, I'll say that skyrmion fabrics meet all the criteria required for reservoir computing. The simulations show clear evidence of nonlinear collective behavior, especially at the 1 gigahertz excitation, and preliminary pattern recognition was observed. Furthermore, there is a scaling path to larger, more observable effects that we can identify. And with that, thank you for listening, and I'd be happy to answer questions.